Hello, this is question 7 from the Spec A MAT paper that they issued in 2009. The game of Oxflip is for one player. It involves circular counters which are white on one side, black on the other, placed in the grid. During a game, the counters are flipped over, changing between black and white. Okay, following certain rules. Given a particular size of grid and a set starting pattern of whites and blacks, the aim of the game is to reach a certain pattern. Each move of the game is to flip over either a whole row, or a whole column of counters. So one whole row or column has all its blacks swapped to whites and vice versa. Okay. For example, in a game played in a 3x3 square grid, if you're given the starting and target patterns, okay, start with that sort of checkerboard, end up with all white. Sequence of 3 moves to achieve the target is flip the first row, flip the middle column, okay, and then flip the third row. Okay, there's probably lots of other options. Right, so consider the 2x2 version of the game with that starting pattern. Draw in the blank patterns below the 8 different target patterns, including the starting pattern, that it is possible to obtain. Right, well, there's no distinction between black and white, so we can just do mirror images of these. So, well, you'll be able to get the starting pattern. So we can have that, and then we can have the mirror image of it, which would be that. If we say we flipped the top row, we'd get that, and then mirror image, we'd get that. If we flipped we can flip one of the columns and say, well, we'll have that, and then mirror image will give us that. And then we could do a double flip, couldn't we? We could flip to get all whites or all blacks. So let's do that one. Okay. What are the possible numbers of white counters that may be present in these target patterns? We've got 2, 2, 2, 2, 2, 2, 4, none. So 0, 2, 4. Okay. Part 2. In a 4x4 version of the game, starting with pattern that, explain why it's impossible to reach a pattern with only one white counter. Right, they've had variants on this theme in loads of MAT papers. Right, so hint, don't try to write out every possible combination. No, we're going to be looking at how many, well, we got an odd or even number of white ones in this. So what we started off here, we got 8. So we start with 8 white. So what happens then when we're flipping something? So if we flip a row, so say we've got, let's do a little table. So we've got white, and then we've got flipped white. So once we flipped it, so say we had a row which had 0 white, 1, 2, 3, or 4. When we flip it, we're going to get 4, 3, 2, 1, 0. So we've got a change here. So the change is 4, 2, 0, 2, 4. So every flip will make an even number of changes. An even number of changes to white. We start with an even number of white, even number of white. So we'll always have an even number of white. Like I say, they've done this sort of thing before in loads of sort of questions, variations on this theme. Always have even number of white. So it certainly helps. We've done a lot of papers for this one, because I think the first time I came across this, I wouldn't have come up with the answer quite so quickly. But like I say, I've seen something like this before many times. Okay, so yeah, therefore cannot, let's just really labour the point by getting exactly what they said there. Cannot have only one white. Okay, that's already on to the last bit. In a 5x5 game, explain why any sequence of moves which begins with that and ends with an all-white pattern must involve an odd number of moves. And what is the least number of moves? Right, this is essentially the same question. So we started with 12. Start with 12 white, and we want to get to all white, so end with 25 white. Then we can do our thing again of white, flipped white, and then the change. So for white we could have 0, 1, 2, 3, 4, 5. When it's flipped we'll have 5, 4, 3, 2, 1, 0. Change is 5, 3, 1, 1, 3, 5. So each flip makes an odd change to white, and we want to get to, we need a total change of 13. Change of 13, which has got an equal number of flips times odd. Therefore, number of flips must be odd. Okay, what is the least number of moves needed? Right, so we need to get to 13 changes. So, I mean, you can't do this in 3 though. I mean, the obvious thing is we flip, say, that row and that row, which would give us columns going black, white, black, white, black, and then we flip column, column, column. I don't think we're going to do better than that. What is the least number of moves needed? Are we going to be able to do better than that? I mean, the most we can change when we start off, I mean, we can't do better than 3 on the first 2 flips, can we? I mean, even if we went for this one and this one, yeah, I mean, if we start, yeah, we can't do better than that. So the most, okay, the most whites we can add on first flip is, I mean, we could add more on the second one. Okay, let's go first 2 flips, because we could say we flipped this one here, then we'd be getting 1 extra white, but then we could only add 1 extra white on the second flip. On first flip and second flip is 1 plus 1. So we'd still have to add another 11. So yeah, we're not going to do better. So therefore, minimum 5 flips, as in we could do 5 plus 5 plus 1 plus 1 plus 1. So we just need a specific example of that happening. So achievable by doing row 2, row 4, column 1, column 3, column 5. So yeah, just put in that first bit, just showing, because you might think, oh yeah, well, we could do a 5, a 5 and a 3 would give us a 13 change, but we don't have any option to even start with any of them. You know, our first couple of flips can only give us 2 at most. So we're stuck with having to do a 1, a 1, a 1, and then we've got the option of doing 2 5s. So otherwise, if I just said, oh yeah, well, I can do this in 5 by doing row 2, row 4, column 1, column 3, column 5, you think, well, maybe there's something better than that. But we can show that there isn't, because we can only get 2 out of the first 2 flips. So we have to have at least 5, and then there's a specific example. So, right, okay, that was fair enough. Again, a little bit on the easy side compared to the actual papers, but that's a fairly typical computer sciencey sort of question that they have in the MAT papers. But again, I suppose I'm caveating that with, it's a little bit easier because I've seen questions pretty much exactly like this in the actual MAT papers that I've already done. So it's like doing a question I've already seen, which does make it considerably easier. So, but still, that's wrapped up specimen A. It'd be interesting to see what specimen B is like, whether it's, you know, more of the same or whether they ramp it up a little bit. But I suppose that's the trouble. Going back to 2009 on this paper, it is going to be quite a lot of duplication compared to what they did in subsequent years. So these ones are naturally going to be a bit easier than the real thing.